Let us try to determine whether the given x vectors here, we have 4 of them, which of these 4 is considered as an eigenvector of the given matrix A, which is a 3 by 3 square matrix. Before we proceed with the processes, there is one important theorem that we need to remember that might help us in analyzing our results later. It tells us that for an n by n square matrix, the number of eigenvalue and eigenvector, which corresponding definitely, is at most n. Okay, and this means that this is a 3 by 3 matrix. We are expecting here at most 3 of these 4 is considered to be an eigenvector. When you say at most, there could be none, there could be 1, 2, or 3, but not all of these 4 are considered to be eigenvectors. That's just a hint of analysis. Don't worry about the fourth vector to be used. It's a little bit longer when it comes to their entries, but of course, just for the purpose of illustration, we're going to show the process of dealing with this complicated vector. Now, how do we determine whether a given vector is an eigenvector of a matrix, specifically a 3 by 3 matrix here? We need to show that there exists a certain lambda, okay, that will satisfy this given equation. You have A times your vector x, so which vector you're going to choose must be represented or can be represented by a certain, or as a product of a certain lambda and the same vector used. And if we could show that the said lambda is the eigenvalue and the vector is the eigenvector of matrix A. Okay, so let's start with A here. Of course, we're going to start with this process. So let's multiply 1, 0, 5, 0, negative 2, 4. That's negative 2. 1, negative 2, 9. With the first vector, a vector on A, you have 1, 1, and 0. Notice this is a 3 by 3 square matrix and your vector is 3 by 1. So we are expecting a result here which is also a 3 by 1 matrix. And we simply multiply them. Let's do it like this. 1 times 1 is 1. This is 0. That's also 0. So you have here 1. Okay? Next, 0 times 1 is 0. Negative 2 times 1 is negative 2. This is also 0. So you have 0, negative 2, and then 0. So that's negative 2. And finally, we have 1 times 1 is 1. Negative 2 times 1 is negative 2. This is 0. So 1 plus negative 2, you have negative 1 here. Notice that our original vector used is 1, 1, 0. So if we could show a certain lambda that can be taken out from this and the remaining matrix will return here, then this is an eigenvector. But when you look at this closely, notice here, okay, one thing that you could see is the presence of 0 here. If this is 0, this should be 0 here as well, because no matter what would be the value of lambda, when you multiply it to the third entry, this should be 0. But since it's not 0, that's an analysis you can say that there is this vector is an eigenvector. But of course, just the purpose of further illustration, let us have this one here. For the first entry, that's 1 and 1. So you could take lambda as 1 so that your first entry is still 1, because 1 times 1 is 1, right? But if you're going to take 1 here, this is still negative 2 and not 1. And of course, as mentioned, this is negative 1, not 0. This is an indication that your first vector and your x vector in A, which is 1, 1, 0, is, sorry for that, is not an eigenvector of your matrix A. Okay? Let's do it like this. Right. Okay. It's not an eigenvector. That's one thing that you also need to analyze, the connection of your entries of your matrices. So let's proceed to letter B. If A is not an eigenvector, let's try to examine if it is B. So you have 1, 0, and 5, 0, negative 2, and 4, 1, negative 2, and 9. You multiply it with your second vector here, we're able to use negative 5, 2, and 1 here. So with that, let's try to multiply this. Of course, that's 3 by 3 times 3 by 1 as well. So you'll have here 1. Of course, we will have 3 by 1 matrix here. 1 times negative 5 is negative 5. Sorry, let's also try to add the rest. What do you call this one? 1 times negative 5 is negative 5. This is 0. That's also 5. So negative 5 plus 5, that's 0. Right? Okay. Next, you have 0 times negative 5 is 0. Negative 2 times 2 is negative 4. 4 times 1 is 0. Okay? And then next, you will have 1 times negative 5 is negative 5. 2 times 2 is negative 4. 9 times 1 is 9. Negative 5, negative 4. 9 is also 0. Notice here that our result is a 0, 0, 0 entries with our matrix, or the vector 0, 0, 0. Let's try to examine if we could represent it like this. Lambda times x, where x is our matrix here. Do you think there is a certain lambda that can be used here? The answer is yes. What if our lambda is 0? If our lambda is 0, that would mean whatever would be the entries here, they will still return to 0 as we are going to multiply our scalar from the scalar 0 here. This would mean we can still accept negative 5, 2, and 1 here. Even if there's no other factors aside from 0 here, or there are multiple factors that can be used in product of 0. Okay, this matches our original matrix, and if we're going to multiply 0 to negative 5, 2, and 1, it will return here. So this is actually the lambda, and this is our vector x. This means it's yes. We are going to accept this one here, where our lambda is 0, or this is the eigenvalue of the eigenvector negative 5, 2, and 1. So it's possible here. Okay, this is because even if the result is 0, 0, 0 and your vector is non-zeros, you can take a 0 scalar for your lambda, and you can just simply copy this one here and still get the same result. So we have 1 already. Now let's continue with our third vector, 0, 0, 0. Let's try to examine how it will look like. So of course, you will have a x still. So your a, let's check it like here, 1, 0, 5, 0, negative 2, 4, 1, negative 2, and 9, with our 0, 0, 0 vector here, this one. Okay? Now, if you're going to examine this further, of course, you can always take the result here. Of course, the result will become 0, 0, 0, right? Because whatever you multiply to 0, it will return here. And you might try to duplicate the same process here earlier with our vector b and say that your lambda is 0 times 0, 0, 0. However, per definition of eigenvalue, okay, for this definition here, the it should be a non-zero vector x. This is actually a 0 vector x because all the entries in our vector are 0. Note that our eigenvector cannot be 0 because it will make our definition meaningless, as it will satisfy all values for lambda. Okay, so it could not be, of course, if your lambda here is 1, so 1 times that, it's still this one, right? It's still this one, right? So if this is, say, for example, 100, your lambda is 100, so you have still this same and the same here as well. In short, you have infinitely many possible values for your lambda, and again, it would again make our definition meaningless. So if you see something like this where the vector being verified to be an eigenvector is a 0 vector, automatically you can say that this is not an eigenvector, because the eigenvector should be a non-zero vector. Okay? Now let's proceed to letter D, and this is where it gets interesting because you have here radicals. But of course, you just need to review the correct processes involving radicals. You have your vector here, 2 square root of 6. Hopefully I could follow. 2 square root of 6 minus 3. Negative 2 square root of 6. I believe it's plus 6. And then you'll have here 3. Okay, so the first thing here is the step that is complicated is of course when you multiply all of this, right? So let's do it like this. Let's have a longer process. So 1 times this, you'll have 2 square root of 6 minus 3. 0 times this is actually 0, right? 5 times 3 is positive 15. Just for the first entry, let's try to simplify it later. 0 times this entry is 0. So you have negative 2 times this entry. So that's positive 4 square root of 6 minus, that's minus because negative 2 times positive 6 is minus 12. And then for the last one, we still have 4 times 3. So we have plus 12 here as well. Okay, again, let's do it again. 0 times this is 0. Negative 2 times negative 2 is positive 4. Negative 2 times positive 6 is negative 12. And then 4 times 3, which is 12. And finally, 1 times this, you have 2 square root of 6 minus 3. Negative 2 times that. So you will have negative 2 times negative 2 is plus 4 square root of 6, right? Negative 2 times negative 2, just like what happened earlier. Negative 2 times 6 is minus 12. Then 9 times 3, which is 27. Let's simplify this first. Of course, this is positive 12. 2 square root of 6, and you will have here plus 12. Alright, next, you will have 4 square root of 6, as this becomes 0. And here, you have 6 square root of 6. This is 15, minus 15. So you have plus 12 here as well. So when we are going to show here, it should return to this one here. So I don't know if we could really show their connection, as if we are going to factor a certain lambda that will satisfy this. Take note that we have binomial terms, or for our entries, the first entry and the third entry are binomial expressions. Once you take out a certain lambda, it should affect both terms here. So if your goal is to make this negative 3, this 12 here, and taking out negative 4, take note that yes, this will become negative 3. However, the factoring of negative 4 will also affect this entry. Okay? So what is best here is actually, you can take out 1, still 1, right? But it will just return to this one here, and the certain vector will not return to this given. As a matter of fact, your third entry for your original vector is 3, and you have here a radical expression. In short, you'll be factoring square root of 6 if it's possible, right? But when you factor square root of 6, take note that your second entry, of course, this will become 6, but your second entry will be 12 over square root of 6 as you factor out square root of 6. So it will not return to the original. In short, this is also not an eigenvector of matrix A. So a little bit complicated here. Again, the goal is to make sure that the result for AX will be equivalent to a certain lambda x with the same x. If it's not, then definitely it's not an eigenvector. This is how we verify whether a certain vector x is an eigenvector of a given 3 by 3 matrix. Thank you very much for watching.